Guys, welcome to another episode of CUDA Education. Today we are continuing on our path of going through all of the examples that we have here. These examples are freely available on GitHub. Links in the description below. If you want to follow along with these examples and have Vulkan running on your machine, check out tutorial number 1 and tutorial number 13. Tutorial number 1 installs the Vulkan API on your machine. Tutorial number 13 installs all of these examples. I assume that you have a Windows-based machine with a Vulkan-capable GPU. For this example and the last couple of examples that we have discussed, it does not require ray tracing capabilities. However, if you want to run the ray tracing examples, which are these examples right here, the ones that start with ray tracing, you have to also make sure your GPU is ray tracing capable. For NVIDIA, that means RTX cards and later or greater. Okay, so the RTX series ray tracing capable. But for this example, which is the computecullandlod, you do not need the ray tracing capable piece, okay, because we're not using the ray tracing extension, the ray tracing features of the GPU in order to run the example. This is just a quick video overview of, my initial foray into this script. And basically what it is, compute shader culling and LOD using indirect rendering. LOD means level of details, or level of detail, okay? I'm still trying to get used to the script. Basically, when we run the script, we get an image, a weird image, I will admit. We get an image of stuff. And basically, we could zoom in and zoom out. We could go around and around, up and down, right? But we get an image of stuff. And we have some statistics. We have total number of visual objects, 26,000 plus. And then we have level of detail statistics, right? Now, this is where things get a little interesting. Really and truly, the level of detail is, really, this is what, when we're talking about level of details, we're talking about this. So I'm gonna assume that, like for these things that are up close, it's the highest level of detail, and then for the things further back, the level of detail is less. And I'm gonna just basically assume that like the things all the way back here, less detail, more detail as we get closer, right? So the closer ones is 135 or so. And then as we get further out, we have less level of detail. We could even say that it's a little bit color coded. We have green, and then it gets closer and closer to yellow, and then it gets orange and then red, right? And so that's the level of detail piece. And then we have the frustum. Now the frustum is basically what the camera can see, okay? The world space of the visual area of the camera, okay? So right now the frustum is, it's everything, right? So we're basically, everything is being rendered, right? Including stuff that is not visible on the camera, right? So the thing with computer graphics and processing and just in general, you want to not process stuff that you don't have to, right? Because you want to save energy, you want things to be efficient, you don't want to burden your compute capabilities, right? And you don't want to waste energy. So you know, if this is the only visual area that we're seeing in our application, there's no reason for everything else, like all of this stuff behind the camera and stuff, to be rendered, right? Because we're only concerned about what's in front of us, right? And this is where this frustum comes in. The frustum, again, is just the visual, the world space, the view of the camera, right? And there's a lot of nomenclature vocabulary dealing with, you know, what is immediately visible to the camera. So what we're going to do now is we're going to freeze frustum. Okay, so we're freezing the frustum. So what we're freezing is basically we're freezing the basically the visual area of the camera, and we're only going to process what is visually seen by the camera, right? And everything else is going to be discarded, right? And again, we do this because we want to save processing. We want to save energy. It's almost like we want to be lazy. We want to not burden our the GPU and all the things involved, our system, with processing things that are not relevant, that are not useful to us, that doesn't help us in any way, because we're not seeing it, where the camera isn't viewing it or anything. So when you freeze frustum, you're going to see now that everything behind the camera disappears, right? Everything behind the camera, above the camera, below the camera basically disappears, right? And we're only interested in, you know, we only rendered what was visible by the camera, right? So again, when we go behind the camera, we don't see anything because we discarded everything that was not visible by the camera. Now, if we unfreeze frustum, we get back the background and everything, and that makes sense because we are now processing everything, regardless of whether the camera can see it or not. Now, if we refreeze frustum, right, we're going to get the opposite of what we had before. So we're going to see the background behind the camera, but then when we turn the camera lens, everything disappears from what we originally had. And that makes sense again because we're not going to process things that the camera cannot see, right? So that is one part of the, you know, what this example is trying to show. Now, so we've kind of done that. The thing is that, yeah. Okay, so that's yeah, I was hoping the counter would change too, but it doesn't change the number of objects. But okay, all right. So that's one part of what this example is trying to show. Now, the other thing is this compute shader culling and indirect rendering. Okay, so I have to spend more time with it. But what it's basically saying is that in the traditional sense, the CPU issues draw calls to the GPU. That's how traditionally this stuff is done, right? Most of these examples, the CPU is issuing draw calls to the GPU, and the GPU draws stuff and, you know, presents to the screen and all of that stuff. In this example, we have this compute shader culling, okay? And what it's basically saying is that, and this indirect rendering. So what it's basically saying is that the GPU is issuing the draw calls and doing the draw calls, right? So everything is being done on the GPU, and also the culling, or like the removing of objects and stuff, is also being done on the GPU side. And we know this from the description provided here, because it says compute shader culling, and the big giveaway is this shader word, right? So anytime we see the word shader, we know we're talking about GPU side stuff, not the CPU, but GPU side stuff. Okay, so compute shader culling, right? So the culling is being done, and culling is just removing stuff and discarding stuff and not processing stuff and all that, right? But anytime we see this shader, we know we're talking about GPU work, right? Or GPU instructions, right? And then the indirect rendering again is sort of issuing the draw calls from the GPU itself. So what I want to do is let's just before we even dive into the source code of the main script, let's just even look at the shaders, right? So we have this one, we have this one, and we have this one, right? So we have the cull shader, which is a whole bunch of stuff. And notice that we have this VK draw indexed indirect command, right? And there's a whole bunch of instructions associated with it, which I'm not going to get into in this video. I just kind of wanted to do a quick overview of I just wanted to do a quick overview of what's going on here, right? So we have this for the cull fragment shader. Fragment shader usually deals with like colors and stuff, and then the vertex shader is dealing with meshes and stuff, right? So this is the GPU side processing, right? So we have a compute shader, fragment shader, vertex shader, okay? And we shall get into this at a later point, but so that's the big claim to fame for this script, is that we're doing compute shader culling, so culling on the GPU side, and level of detail using indirect rendering. So the issuing and the rendering and everything is on the GPU side, right? So it's just showing that you don't necessarily have to do everything on CPU side. You could push things to the GPU, and the GPU can also do it, which at this stage in my development and my understanding, I can't fully appreciate it, but it's a tool in our toolbox, and I'm sure it will become useful for us in the future. So finally, I just want to do a quick run through of the actual script. And remember, this script is freely available on GitHub, and you can install and run this on your machine, assuming you have a Windows-based machine with a Vulkan-capable GPU. You could check out tutorial number 1 and tutorial number 13, which will help you to install it. These are video tutorials that will help you to install it on your machine. I will also say that this is the easiest way for you to get Vulkan up and running on your machine, right? I've tried all the other examples. This is the easiest, most straightforward. It is literally a video tutorial, a video walkthrough of installing Vulkan on your machine. Okay, so and installing these examples, right? So to get from zero to hero, my examples, bar none, is the best way to do it on the internet. Okay, I make no apologies about that, and no equivocation about that. Okay, all right. So let's just get into it. So we have some Android processing for people that are our Android friends, which doesn't concern us. Notice that we have our fixed Frustrum variable. So initially the variable is set to false. So when we run the code, everything is being processed, and we know that because when we move the camera, there's stuff going on behind us and all of that stuff, right? Now, if we change this to true, right? So we're just fixing it to what is visible by the camera, right? So if we run this now and we set it to true, why am I getting errors? Hold on. Oh, I'm getting errors because I still have the window open. Okay, so let's run it. I still had the previous application open. Okay, so now when we freeze it from the jump, notice that aha. So notice here when we freeze the frustum, we get only level 5 detail, which I am going to assume is less you know, the least detail. And you could see that because all of them, first of all, it's color coded red. And then you notice that you don't have as much detail on the frustum, right? And you have 13,000 objects just on level 5 detail. And then also notice that you don't have anything that's like behind the camera and all of that. Let me rerun this because maybe I moved the camera. I don't know why it's doing it like this, but whatever. Okay, but we could see we have 132,000 objects, and we see that the objects, it's less level of detail, right? And we're kind of only rendering what is seen by the camera, and everything else is just not there. Now, if we unfreeze frustum, we get back our original thing and our level of detail, right? But then, you know, things change, right? But again, we could see that we have, when we default the freeze frustum to true, that the level of detail is definitely down, right? So LOD 5 means less level of detail. LOD 0 means full level of detail, right? Let me put it back to false just to keep it default, but I will probably play around with this some more before we're done with this video. Okay. Right, LOD model. We're not gonna fight that battle right now. Indirect command buffers. Indirect draw statistics. Store the indirect draw commands containing index offsets and instance count per object. Resource for the compute part of the example. Yeah, let's not dive into this too much right now. Notice that we do have our fences again, and from previous videos, you guys know that once we see fence, we're talking about CPU to GPU, CPU to GPU synchronization. So synchronization fence to avoid rewriting compute command buffer if still in use, right? So that makes sense to us. We're not going to rewrite the command buffer if we're still using it, I guess, for the previous frame or what have you, right? And then we have compute semaphores, right? And you guys know compute semaphores or semaphores. We know that semaphores are GPU processes. So synchronizing between two GPU processes, right? We're not going to dive into it too much right here. So let's just see. Semaphores. Used as a wait semaphore for a graphic submission. Used as a wait semaphore for a graphic submission, right? So I guess he commented this version out. The difference between the two is that this one has compute. Okay, fine. Right, so we have our semaphores here. View frustum for culling invisible objects, right? So view frustum for culling so this makes sense. Culling invisible objects. So the things that are not seen by the camera, we are discarding, right? We have our camera stuff here. We have destructors for all of our objects that we need to clean up. Good housekeeping is always a excellent practice. Get enabled features, load assets. This is the object that is of interest to us. We have descriptor pool stuff, prepare graphics, layout, buffers, pipeline layout. Input states we still have to sort of dive into. I may or may not dive into it with this script, but that's also a topic of conversation. Vertex input bindings, vertex attribute bindings. Let me move this. Indirect and instance pipeline. Yeah, we got a lot of work ahead of us, guys. We have a lot of work ahead of us. Prepare buffers. Indirect draw calls. Right, so I believe when we talk about indirect draw calls, we're talking about, submitting draw calls from the GPU instead of the CPU. We've seen this initial release barrier to the graphics queue so that when the compute executes to the first, it doesn't complain that there's a lack of release or acquire. Okay, so that is that. Yeah, not sure about that right now, but we'll leave that alone. All right, get a compute capable device queue. So we have touched on queue family before. So here we're trying to get a device that has the compute capabilities, the queue family with compute capabilities. Remember these algorithms, everyone has a different GPU, and everyone, some have older GPUs, some have newer GPUs. Some, the queue family, the compute is separate from the graphics. Other GPUs, the compute and graphic capabilities is the same queue family. So, you sort of have to bulletproof the script, for different for different GPUs that it might run on, right? And that's kind of what makes this stuff challenging, because you can't make assumptions on the capabilities of everyone's GPU, right? Because everyone's GPU is different. So you have to you have to make sure you do things properly and correctly. Layout bindings, all of this stuff. Lots of stuff going on here. Semaphores to order compute and graphics submissions. Fences to check for command buffer completion. So again, fences is CPU to GPU. Semaphores GPU to GPU. So this is like usually presentation stuff, and then this is the CPU side stuff. So we're submitting command buffers, and the CPU is submitting command buffers, but it has to have a way of knowing whether the command buffer has completed, right, before it starts doing other stuff. Mesh containing the LODs. Okay, wait for rendering finished. Submit graphics commands. So we've kind of seen this before where we have the submit graphics commands, submit compute commands and then submit graphics commands. So we have seen this movie before, right, guys? This is nothing new to us. Notice though that in this case, we had a submit, we had the compute and the graphics commands, right, in a previous example. But notice that this is all dealing with no, well, actually no, we have our fences too. No, we have our fences too anyway. Yeah, we'll get back to that. And that's pretty much it. 1 second. All right, I do want to look at something quickly. So I want to compare this stuff with what we did in what we did with okay, never mind. never mind. We'll fight that battle another time. Never mind. What I did want to do though. Okay, so right. So let's just run our application again real quick. All right, so we have our application, we have 31,000 objects, right? Total. Let's do level of detail 0. So we're doing max level of detail of 0. Let's see what happens when we do that. All right, that just affects the statistics, right? Because if we do like yeah, that just affects the statistics. Okay. All right. I'm not going to worry about that too much. All right. But anyway, guys, so yeah, as always, we're in a work in progress. But, you know, we have a lot of work ahead of us to do. This is CUDA Education. We are trying to basically dive into this compute shader culling and level of detail using indirect rendering. We definitely have a lot of work to do, and we kind of have to dive into this piece by piece and figure out, you know, the main script and also all of these shaders and what it is trying to do. I apologize in advance if I sort of misspoke in terms of the actual description and what this script is trying to demonstrate. But again, we're just figuring our way through this application. Again, guys, I will tell you, this tutorial number 1 and tutorial number 13, the best, most straightforward, and efficient way to get Vulkan, and a bunch of examples that you could use to learn Vulkan. The best way to do that is through my approach. The absolute best way. Straightforward. You could start learning Vulkan relatively quickly and start tinkering with quality code. So anyway, guys, thank you for watching. This is CUDA Education. Have a great day. Goodbye.